Hi, I'm Phineas and he's Ferb, and we're the Unstable Fluid podcast.
Oh, every time I have no idea what you're going to come out with, and you come out with something ridiculous. Hi, Kat.
Hi, Thomas. How's it going?
Hi. Not too bad. Busy, but yeah, that's life at the minute. We got new PhD students in the department today, which is interesting.
Oh, is it welcome week?
Yeah, it's Freshers Week this week, and they've had their induction today, and then tomorrow they get to come and listen to all of us that have just done first year actually give talks on what the hell it is we've been doing for the last year, and then they start on Tuesday.
That's cute that they get to learn, sort of what someone else has been doing in the meantime.
Yeah, it's kind of an opportunity to let those of us that have been doing it for a year kind of get practice of a conference talk type thing with a friendly audience.
Nice. Yeah, Sambi used to do something similar, call them transfer talks, where it's you progress from the first year to a PhD student. But I think those happen around mid-October, so after a few weeks of getting settled.
What have you been up to anyway?
So I have seen this must be my 9th Freshers Week. No, 10th Freshers Week. Yeah, 4 at Cardiff, 5 at Bath, now 1 at Warwick.
Yeah, but you're now no longer a student.
Not according to the helpers around campus who kept asking if I was there for my first year tutorial as I tried to get to my office today. I went into the office. I've been trying to do this thing now that I have a job, apparently, where I dress a bit more like I'm going to work. I have an entire work outfit. If anyone's ever seen me give a talk or something, I have smarter clothes so that I feel like I'm in the right vibe for work. Normally, I go to the office dressed up like I'm going to work. Today was a bit of a building furniture and putting my computer back together day. So I was in dungarees and a jumper, and clearly...
You look like the average 18-year-old Green voter.
Yeah, that was the vibe. Which I'd accept the compliment. If not, please don't make me go to first year stuff. I don't want to be a first year undergrad again. Thanks.
No, I didn't really do societies in the first year of the PhD, and I went yesterday. I went to the Freshers Fair to actually see what societies exist in Cardiff.
Oh yeah.
First mistake was I went at lunchtime. So it was busy. It actually wasn't too busy inside. Problem was when I left the department to go and actually go up to the Students' Union and go to the Freshers Fair, it was kind of drizzly. On the way back, the heavens opened. So I was just drenched for the rest of the day, which was not the vibe. That was just reminding me that I just really hate Freshers Fairs.
I like the free stuff. There used to always be Domino's at Cardiff Freshers Fairs.
Yeah, they had that, but I had just had lunch.
That was your rookie mistake there.
Also, I'm discovering I think I still have I don't know. Maybe it's trauma from doing academic representation stuff, but there was just this urge to just avoid those stalls entirely before someone could try and get me to sign up for something.
You just accidentally end up as a rep for some random society that you didn't know you were part of.
I have a friend who ended up as a sabbatical officer by accident. He signed up on a joke, and then the other people running were, shall we say, not the best candidates, and he ended up actually having to campaign.
Oh dear. That's
He was really good at the job, but he did not want it in the first place.
Yeah, staying away from any sort of risk of responsibility or Freshers Fair. I made the mistake of going and looking at the campus gym because I haven't checked it out yet, and then Warwick has a climbing gym in its on its campus, which is really cool. But yeah, going this week when it's Freshers Week and all of the undergrads are signing up as well was a terrible, terrible mistake. But hopefully it'll calm down over the first few weeks. Once the excitement kind of dissipates and campus calms, I'll figure out what's the good routine. So what else is news with you, Thomas? Anything exciting?
Not massively. It's been fairly average, though actually to be fair, as I spent most of the last month working on figures for my first paper, and pending supervisor approval sometime after next week, when she's had the interview for her funding thing, pending supervisor approval of the figures are done, which means I can start writing the damn thing.
That's exciting.
And it also means I can do something else with some of my week. I'm really bored of these figures.
That's fair enough. I think there's only so much formatting that I can be bothered to do sometimes.
Yeah, I mean, there'll be some tweaks to formatting, but like I've just spent the last month trying to get the data to display in a way that makes sense.
Visualization is actually like an entire topic, learned skill thing on its own sometimes, like how you represent things.
I maintain it is something that people should actually be taught how to do.
Yeah. If you would like our audio-only formatting to discuss visualization, let us know.
I mean, I literally made a video about this.
Oh, did you make a video about it? You should advertise your video.
Yeah, it's on YouTube. The links to our stuff is below. You know that.
Yeah. I don't pay attention.
Oh yeah, because I do all the uploading.
I check the Instagram and make sure that you tag me properly.
Fair point. Fair point.
If anyone was
Way
wondering
to
the
at
division
me.
of labour, it is unfairly weighted towards Thomas, which we appreciate greatly.
It's fine. You pay for the hosting.
I do indeed. Speaking of paying for things, I bought my hardbound theses this week.
Oh.
It was terrifying.
Nice.
I was so scared I'm still scared. I haven't seen them yet about the margins because you hear horror stories about it not being on the page properly. But hopefully the format, the style file thing that I used should hopefully make it look all right. But yeah, I have ordered one for the department as a gift, one for my supervisor, one for me, and two for family members. Hopefully in the next 2 weeks or so, I'll be able to actually have physical copies of my thesis, which is wild.
That I am sure is going to feel good.
Yeah. Just
a physical manifestation of the PhD.
Yeah, that I can never look at in case I find a typo.
Just to hope the typo's not on the cover.
I'm pretty sure. They made me fill out an entirely separate form for what goes on the outside of the book. So I'm pretty sure at least like my name is spelt correctly, my title should be spelt correctly. It'd be exciting.
So this may come as a shock to people listening to the podcast, but we have actually sort of done a little bit of prep so we can actually talk about some science rather than just going off on a tangent about all of the things that we normally talk about to do with academia, because this is meant to be a podcast about, fluids, not just instability.
Is it called instability if we're referring to like mental unstableness?
Well, you talk about having like a stable mental health and
unstable, not instable.
Yeah, but I don't do words. That's why I do science.
This is me just like trying to hide from you making me do science and like, let's just segue to etymology real quick. If anyone does know why it's instability and unstable, let us know, please, because I am curious. But yeah, there's some fluids, some science, some like actual maths, less maths, more science.
Yeah,
but still.
actual maths.
How dare you?
What's a number?
It's this thing that is a concept and also helps to quantify.
Cool. I haven't seen one in a while.
Yeah, I mean, my undergrad course, I think we spent an entire lecture discussing what is a number. So like right at the beginning, just being like, what does it mean to count? What does it mean to number? Everything's like arbitrary. I think that lecture in particular really belonged in philosophy, but it was a great time.
So what mathsy, sciencey stuff are we talking about today?
Ooh, good question. Was I supposed to do something? No, I'm kidding. Basically, I want to know how space works. So I'm going to use...
We could be here a while.
I want to bring up fluid dynamics-y things and see how they fit in space, because I think space is fluid. Is that a fair assumption?
Yeah.
Yeah.
You can use a lot of fluidy stuff in space.
Yeah, there are like two things I'd say that the average maybe person knows about the universe. Maybe they don't. Maybe this is just me watching too much Big Bang Theory. But like Big Bang and then things are expanding, but also it's infinite, right?
Yeah. The cosmologists I think some of the cosmologists still disagree on that one, but yes, Big Bang, expansion, but the expansion is happening everywhere. It's not like expanding from a single point.
Yeah. Okay. How do you get expansion everywhere?
Space itself gets bigger.
So it becomes less dense?
Yes.
Ah. Isn't that a nice segue onto the topic of today?
Yeah, I'm not going to go into the whole heat death of the universe thing, but essentially, yes, space get bigger, energy density go down, eventually heat death.
This is a happy, fun podcast, Thomas. How dare you bring heat death of the universe into it? That's a later section.
That's where the podcast gets more unstable.
Exactly. But no, so density as a concept, right? Like everything sort of has a density. I'm going to be really hand-wavy verbally with this.
Yeah, I think everything has a density, yeah.
Yeah, it's a reasonable
Do you want to explain
statement.
to normal people what density is?
Basically how much stuff is in a given amount of space. And you can think of it as, you said, steel, something that's really, really dense. There's a lot of like particles, atoms, smushed into one small space together. And density is something that comes up loads in fluid dynamics because it's obviously like air, gases, very undense.
Yes, generally speaking,
Sparse.
very undense.
What's the word for undense? Is it sparse?
I mean, you could use underdense or low density, something along those lines.
Yeah. Whereas liquids like water or like oil or something, that's going to be a lot more dense than a gas. So that's
More stuff in given volume.
yeah. And then solids again, other directions. And there's more like nuanced distinctions between gases, liquids, and solids that I'm sure the physicist can get into. And
Yeah, for example, sponge, not very dense, why it floats. Because less dense things will float on denser things, assuming they're liquids or gases. Assuming a fluid.
And then obviously like there's no such, or there isn't in the real world necessarily a fixed density of a given thing because you can smush particles or elements of it closer together to compress it. Fluid dynamics, however, and I'm not sure how it works with astro, I would guess similarly. We tend, although I'd guess the opposite actually. We just kind of ignore density variations in something, so we tend to like study incompressible flows. Like compressible flow is an entire separate subject.
Yes.
To sort of, if I just want to look at how a bit of water moves through a pipe, typically it's not under such extreme force that the compressible effects of it are going to change the density of the fluid throughout the pipe, unless it's going at very, very, very high speeds.
Yes, in most real-world applications, you're dealing with incompressible fluids.
Correct.
Things that maintain their density most of the time. Astrophysics, a little bit different, mostly because we're a lot of the time dealing with gas in space, and if you can shove more of it into a given region fairly easily, but your densities are fairly low to begin with. Like, generally speaking, less than an atom per cubic centimeter is cosmic gas.
Oh, wow. Okay.
Like less than an atom per milliliter, essentially. But yes, density is a thing. When we're dealing with things like water, we generally consider it incompressible. Air, also most of the time.
Unless something's moving really, really fast or there's a big force on it. So if you're going to look at supersonic planes, so actually planes are always a fun example to go to when you talk about modeling air and fluid dynamics.
Yeah.
But yeah. If
We're not explaining plane wings again.
I like it. It's interesting.
We did it before.
Fine. But yeah, when you're looking at supersonic, it's moving so fast that the air around it starts to be realistically modeled as compressible. Whereas underneath that sort of speed, it's all basically the same. So it's not as important.
And to be fair, those are the sorts of cases where in astrophysics in space you would be then dealing with actually really caring about the fact that density is changing, because we also get shocks, which is what you get when planes go supersonic.
Wait, in space?
Yes, we get shock waves in space.
What is being shook?
The gas.
But there isn't gas everywhere, is there?
No, but if you've got a cloud of gas and say a galaxy comes in and hits it, fast enough. If it hits it faster than the speed of sound in that gas, you'll get a shockwave.
No, okay, sorry. I was thinking about spaceships.
Oh, okay. Yeah, no.
Okay, I was like...
We typically don't fly spaceships fast enough to cause shockwaves in gas clouds in space.
See, this is something I wouldn't know.
We also typically don't fly spaceships into gas clouds, mostly because there aren't any in the solar system of any real that matter in any way. Should we explain actually what a shock is? Because we've kind of just launched up with shockwaves.
Yeah, go for it.
So, shockwave, or a shock in fluids, is what happens when there is a disturbance in the fluid, in the flow of the fluid, that happens faster than the fluid can react. Mm-hmm. Generally speaking, you could take this as the speed of sound in the fluid. So if a thing, say a plane, moves through the air faster than the speed of sound, you will get a shock at the sort of leading edge of the plane because the air can't get out of the way fast enough. And I presume this works the same in atmosphere as it does in astrophysics, which is that you will tend to get shock. In astrophysics, you'll get shock heating. So the gas will basically, as the density rises, its temperature will rise, caused by that shockwave, and then turbulence happens and Cat's equations break.
Yeah, I was going to say, we don't get to that point because, like, I personally don't study compressible, so we don't get those sorts of shockwaves. Yeah, and as soon as you hit turbulence, go get an experimentalist or a scientific computer person or someone who does cooler fluids than me, I guess, if you listen to people on YouTube. There is actually, speaking of YouTube, shameless promotion to the TEDx talk on supersonic, I think it's called Sonic Booms, but it's narrated and written by my old fluids lecturer from Cardiff.
Nice.
So, yeah, she did her PhD on sonic booms and she's really cool. So that is a cool video that people could check out. But yeah, essentially, if you think of it as when you drop, you make a splash or you make a ripple in water, right? Like the waves generate outwards from the impact site. If your impact site is moving, those ripples are going to generate outwards from where you are, but you're essentially moving faster than those ripples coming outwards.
Yeah.
So it's like you're affecting the space behind you, which is why you can, like, you see the sonic plane before you hear it. Same with thunder and lightning. No, opposite with thunder and lightning.
Yes. You see the lightning before you hear the thunder. Yes.
Yeah.
So that's density. That's shockwaves, which we didn't overly plan to comment on. You did have another fluidsy thing you wanted to talk about today.
I just had my random segue before you disappear off density because I did some homework and I did some looking at where we sort of... Don't pull that face at me. The readers can't see it.
They can't see it. It's an audio format.
Very rude. He looked surprised. But essentially just looking up, like, okay, where, when, how, why, which of our brilliant white men from Eurocentric history discovered density. So the two that are currently named, and again, I don't know if they are actual pioneers or if Wikipedia is just focusing on the ones that we all seem to know. But can you tell me the stories relating Aristotle to density? Or the story relating Aristotle to density?
Is this the golden crown in the bathtub thing?
No, but that's my next. That's Archimedes. You can have that one for free.
Okay. Then no, I don't know.
Aristotle saw that boats that were carrying heavy loads and then being sailed upriver would be able to float on the sea, but would start to sink once they hit the rivers. And he realized that the fresh water in the river must be less dense.
Yeah.
Than the salt water in the sea. And kind of came to the conclusion that the salt in the water affected or increased the density. But yeah, they were having this issue where the boats were like sinking lower in the freshwater rivers. The Archimedes story is using fluid dynamics. I would say like density of solids, so it's not really a fluidsy story with the crown.
Yeah.
But essentially he submerged, or story goes, he was in the bath and some king was asked everyone to be like, how much gold is in my crown? And Archimedes noticed that as he got into the bath, the water Archimedes. Archimedes noticed that as he got into the bath, the water level rose. So realized that he could measure that by knowing how dense the water is, figure out how much water there was. And if he submerged the crown in water and saw the water level rising, he was able to determine the exact volume of the crown.
Yeah, and then by knowing what the density of gold would be, you can then find out the mass.
Yeah. And that's why we get the whole Eureka thing from. Fun story. I would say less fluidsy, more just like fluids. It has applications to other things.
Yeah, that one's less fluidsy, more just physics.
Yeah, but those are my sort of fun history facts with Cat section done.
I'm not making a jingle.
Spoil sports. You'll get bored of like PhD work and need to procrastinate at some point, and then we're going to have...
If anyone wants to send us a jingle, by all means.
Jingles for all of the segments. My one other fun density fact, which I just think is really cool, and I remember learning this in Mechanics 2 undergrad, is do you know what percentage of an iceberg is above water?
Not very much of it.
Gonna guesstimate? Give me a percentage.
Somewhere around 12?
10.
Okay, I was pretty close.
Yeah. So as water, you would think like, right, so it's exactly the same water, I could freeze it into ice. You would expect the same density, but the freezing process expands it. So ice is less dense than water. And ice is 90% the density of water. So if it's the same water that is used, it's not added salt or anything, 10% of it is going to be above water, which is why, things like the Titanic, or when you see an iceberg, it's like you're only seeing 10% of the entire body. The center of mass is much, much lower. Yeah,
it's like all those memes that have got like the tiny bit of iceberg above and then the massive amount of iceberg underwater, and it's like what they tell you in school, everything else about the subject.
Yeah. But then what they told me in school was icebergs. So leading on from density. So as we say, space is a little bit more density sort of matters, maybe compressible flow density matters. When we stop thinking of fluids as fluids and we start applying the same principles to other areas of study or the world, we start caring more about density. And if you think about a great example of this is crowd control uses fluid dynamics, because you start to imagine the people as little particles of fluid and they tend to start to behave like a fluid.
Yes, we've actually touched on this briefly in a previous episode.
I have like 5 fun facts and that's it.
But yeah, like there's like crowd control and traffic flow and all that sort of thing you can model with fluid equations.
Yeah, and you can say like, when there's a traffic jam, is a really high density area, whereas when it's just you on the road, it's a low density area and that sort of thing. But generally what you'll have is like things don't like being in high density areas. If you've ever been in a crowd, you're typically looking for, like you as an individual are looking for the biggest space to move into.
Yeah.
And particles do similar things where they want to kind of spread out. And that spreading out when there's no additional forces kind of motivating it is diffusion. Is my next fun fluidsy thing.
So what is diffusion other than spreading out?
Basically that. So it's when you have things going from a high concentration area to an area of low concentration.
If you drop milk into tea, it spreads out through the whole mug.
That is a good one. Yeah. So it's essentially slowly diffusing. I mean, there's going to be something about milk and tea that the thermal convection is going to be taking over there a little bit. Just to say, I tell you what it is. My favourite drink at the minute when I'm not feeling like I want to have a big one is a shandy. A shandy is about half the glass is lemonade, and then you top the rest of the glass with beer or cider or like some other fizzy drink. And you've got the densities are like sort of similar, but not so much so. I think lemonade is actually more dense, so it sinks to the bottom. But in between the two, what you get in the glass is this really cool gradient from clear to like gold. Because the two liquids kind of diffuse. And again, there's going to be bubbles, there's going to be other things sort of affecting it. But generally speaking, you have this nice diffusion, and then you get this cool gradient of colour, which I think is really neat and want to start doing with other drinks because they just look fun. Again, spacey question is, are there things in space that diffuse? Because you have like this big expansion, right? But if that's everywhere every time. Diffusion is more concentrated to outwards.
Yeah, so we touched on expansion earlier on, and yes, the entire universe is expanding. That expansion is very easy to counteract locally, because gravity, if it wasn't, then nothing would exist, because gravity would not have pulled everything together. So on smaller scales, you can kind of ignore the expansion of the universe. It doesn't really matter. One of the best examples of things like density and diffusion and that sort of thing, and how it actually really matters in astrophysics, is something called an accretion disk. So if you've seen the movie Interstellar, you'll remember the black hole. If you haven't seen the movie Interstellar, just go and Google, look up the image of the black hole from Interstellar, and you'll basically see a black circle with a bright band across the middle of it, and then a bright ring around it. Now, the ring around it, that's just gravitational lensing stuff we don't have time to get into at the minute. The disk is the important thing. So you've got this massive disk around the black hole that is just gas and dust moving very, very quickly. And it's essentially, you've got it's that sort of diffusive motion and viscosity, which is how much the fluid sticks to itself, basically causing a massive amount of friction as gravity affects it, causing it to heat up a lot, to the point that an accretion disk around a black hole, assuming that it's in a state where it's essentially feeding the growth of the black hole, can be one of the brightest things in the universe and outshine its entire galaxy. And accretion disks show up everywhere in astronomy. Around black holes is one of the most spectacular, but it's how stars get most of their mass onto it. So your gas cloud will collapse under gravity, become denser, and eventually end up with a sort of like dense pocket with a disk around it. I'm not going to go into the details of how angular momentum is conserved to make disks, but
that was going to be my question.
It's angular momentum conservation, and I will talk at length about this in another episode, but we don't have time to get into that today. That's why you get disks everywhere in astrophysics, in space. It's why the solar system's flat, is you end up, as the cloud collapses, angular momentum is conserved and the thing flattens out into a disk. And yeah, you get that sort of viscosity and diffusion of the gas that then builds up your star and actually gets it from dense protostar to actually fusing hydrogen and making light. And we are made of the leftovers. Like that famous phrase, like, we're made of star stuff. We are, because like everything in the solar system that is not the sun is leftovers from the formation of the sun. There's plenty more I can say on things like planet formation and angular momentum conservation, but not today.
I realized that I was struggling to think of examples of diffusion, and like literally squash, because we call it high concentration squash. It diffuses. Sorry, diluting juice for the Scottish.
I wasn't going to say it. I was wondering if you were going to call me on it.
Yes, of course. I was literally telling someone the other day about, like, we were talking about languages and regional uses of, I think we were saying where uses the word spud for potato.
Yeah.
Yeah, but I brought up diluting juice because I would call it squash. Someone else called it cordial.
So they shop at Waitrose.
No comment. So yeah, but it was that, like, when you have squash, essentially what it does is it will just diffuse throughout the thing. You don't have to stir it or anything. There's no additional forces. It's not thermal convection because you don't have like heat transferring it. So squash is a really good example. If you want to go look at what diffusion looks like, blackcurrant squash in water is quite fun.
Yeah, I don't know how I didn't think of that one as well. It is kind of the classic example.
Yeah, as I say, we did our homework. We didn't do it well.
The dog ate mine. I don't have a dog.
Typically, though, so diffusion is like presumably quite important. If you like, accretion disks are everywhere in space. You are kind of considering diffusive motion quite a lot. Do you get other things like convection and those sorts of effects? Dispersion?
Yeah. So convection is definitely something that we do get. convective motions are of particular interest to people who are interested in how stars actually work inside.
Okay.
So, I'm going to have to try and remember which one this is because it varies depending on the mass of the star, but I think it's low mass stars. If you've ever seen a picture of the surface of the sun,
yeah,
it's got this sort of like almost cell-like structure where you've got loads of like wiggly shapes on it. And the reason for that is convection. So in the core of the star, in the core of the sun, you've got nuclear fusion happening, hydrogen being fused into helium, releasing some energy with every reaction that happens. And there's a radiative region inside where the density, coming back to density, where the density is so high that the light that is emitted by these reactions can't just stream out. It like only gets a little bit and then gets reabsorbed, and it sort of works its way out slowly, being absorbed and re-emitted by particles until it reaches a certain amount of distance through the star where the density gets low enough that it can start to be kind of retained thermally. And what you get is naturally a hot region closer to this radiative core. And that hot gas has cold gas above it, and convection happens. So the hot gas rises to the surface of the sun, where it can then emit that light into space, cooling that gas down again, and the cycle continues. The cold gas falls, the hot gas rises. And that's why you get these convective cells on the surface of the sun. And if people are, I guess, sort of real world example of convection would be a radiator. The idea that heat rises in your room. Upstairs tends to be a bit warmer than downstairs because the heat goes up. It's the same thing just happening on a much, much larger scale at much, much higher temperatures. At least I really hope they're much higher. If it's like 10,000 degrees in your house, you have a problem.
Yeah, maybe turn your heating down. That's bad for the planet and your energy bill.
Yeah, I think, to be fair, I'm not sure they'd be able to turn it down anymore because I think they probably would have vaporized, but... But yeah, so convection is a thing, and you get it on insanely large scales in like the sort of on like the thousands of light years scales that I work on with my stuff with convective motions around galaxies. But I would be lying if I said I fully understood exactly how that works. Ask me in a year. I'm moving on to stuff to do with thermal conduction.
Yeah, I've never thought in depth about how convection works. Like, so typically we tend to see the like convection diffusion equation or advection diffusion equation in maths a lot more, where you have sort of a convective term and a diffusive term. And I'm probably going to get shouted at by someone I know by saying, like, I know how diffusion works, but I don't really pay attention to the convection side where you don't have this like thermal element to it.
Were we going to talk about something else? I forgot what it was.
Did you see the moon?
No, it was cloudy in Cardiff.
Ah, it was so cool. What was it, like last Tuesday, I think?
Something like that.
It was so cool. So we had the super harvest moon?
Wait, okay. Before we go into this, the whole like harvest moon, blue moon, strawberry moon, all this nonsense, it means nothing astronomically. It's from something called like the Farmer's Almanac. Like it means nothing. So like when there's like strawberry moons, like the moon is not pink or red or whatever.
I mean,
if
it looks
red,
pink.
It's an atmospheric thing. It has nothing to do with the moon.
I mean, I'm not suggesting that we paint the moon on specific days, but like it's still a cool thing to commemorate.
The supermoon is a thing. Supermoons are a thing.
Why does that get to be a thing and the purple moon doesn't get to be a thing? I want a purple moon.
The supermoon means something physical.
What does it mean physically?
Okay, so the moon orbits in an almost circle. It's not quite a circle.
Is it a squished circle?
It's a slightly squished circle, and one end of the squish is closer to the Earth than the other. And when it is at the closer bit of the orbit, that's when when it's at a closer bit of an orbit, that is a supermoon because it is slightly closer and appears very slightly bigger. Not big. It's not bigger enough to be like noticeable.
Mm-hmm.
Like it's very slightly bigger. It's very slightly brighter. It's not actually enough for you to notice, but it's one of those things that gets reported like, oh, it's a supermoon tonight.
Yeah, I mean, it looks bigger. Like
a lot of the time when it looks bigger, it's due to essentially like an optical illusion because of the atmosphere.
Interesting.
Or the sort of placebo effect of being told it's bigger so people think it's bigger when they look at it. Basically, human psychology is a bit weird. Yeah, I know what I said.
Okay, sorry. But like specifically, like I remember on Tuesday because we were driving and like I think I suppose it looks lower when it's bigger when it's lower as well, rather than like up high in the sky. Does that have a different? Yeah, I think I saw it when it was quite low down. It was early in the evening, but it was huge and it was really cool. I get very excited about full moons. It just made me happy. So supermoon, no. Blue moon I thought was like, not because of the color, it was because it's a rarity. So it's like if the season lines up in a certain way.
I think it's the second full moon in a month, which can happen. Like, it's not super rare.
Yeah.
It's because the moon's orbit is, I think, about 28 days. And all of the months are at least 28 days long.
Yeah.
So you just basically, like, normally you'll get like a full moon on maybe like the 2nd and then a full moon on the 30th. And the second one is a blue moon.
Okay. Yeah. Because that's where the phrase like once in a blue moon comes from, in that once in a rarity, but not impossibility.
Yeah.
Also, minor segue of like, Thomas, do you know the pigeonhole principle in maths?
No.
Okay. Just, it reminded me of this. If there are 13 moons in a year, full moons in a year, then you have a pigeonhole principle where if you have, say, 10 pigeonholes and 11 pigeons, one of those pigeonholes is housing 2 pigeons.
Yeah.
So if you have more stuff than places to put them, someone's going to be sharing. Is essentially and there's a, it's said more mathematically, but that's the pigeonhole principle. And I don't know whether it comes from like actual pigeons or like pigeonhole meaning like where letters go in an office. I assume real pigeons because pigeons are cool. We had the super whatever the hell it was at Farmer's Almanac thing. The harvest moon.
That thing. There was another cool moon thing at the same time though, wasn't there?
Oh yeah, but that was at like 3:45 to 4 in the morning, so not many people caught it. But there was a partial eclipse.
Partial lunar eclipse, presumably.
Yes.
Yes.
There was a cutout of the full moon.
Yes, as opposed to a partial solar eclipse, which is a cutout of the sun.
It was 3:44 in the morning. You tell me, Thomas.
Yeah, so it's the Earth's shadow partially obscuring a bit of the full moon. Yes. Because it and the sun were in the right place.
Yeah, and do you know why it always looks a bit blurry?
What, the partial lunar eclipse? I do. I'm pretty sure I do.
Because it diffuses.
Yes, the light diffuses through the atmosphere.
Which is what we're talking about this episode, so my fun fact fit in with the episode.
Yes, slightly different diffusion, but yes.
It's still diffusion. Light diffuses, spreads out.
We're not describing light as a fluid.
Aw, please. Maybe some of our listeners subscribe to Bohmian mechanics and they want particle-based light.
Particle wave duality, which again we don't have time for today.
We made like 3 people really happy bringing it up. Okay, so
yeah. This is really just giving us a list of things that I have to explain in future, isn't it?
I'm just going to keep mentioning random physics facts, and then you're going to have to correct me because otherwise I'm going to go off on tangents.
Yeah, it's okay. We'll have to write them all down and cover them in a future episode, which. I think, yeah, if you want us to cover random fluidy physicsy things in future episodes, then you can always, I was going to say write to us, but...
You can write to us in the form of a social media message via one of our things or our email. We have an email. I forgot we had an email.
It's in the show notes or on screen. All of the social medias and all of the email-y stuff are on screen or in the show notes /description. feel free to send us things.
This is the bit where we say don't forget to like and subscribe.
Yeah, don't forget to like and subscribe. Send us things and I will read them because Kat won't.
Yep. I will hear about them through Thomas.
And if you want to send Kat something, then I don't know, try carrier pigeon.
I do like pigeons.